mentioned before, my name is Jeremiah Baker. Work here at BRNE as a consulting engineer, focusing on our clients in Houston area. I've been working at BRNE for about 4 years now, and one of the features that I've gotten to play with a bit more is kind of what we're going to be talking about today. So we're going to look at some of the new IPR calculations that ProMax can do, and how that will allow us to do what's called Downhole Nodal Analysis in ProMax. So we're going to start off with a bit of an introduction and then move from there. But before I get started into the material, I did want to point out that you do see some contacts here on the main page. If you ever have any questions about maybe wanting to apply something that you learned here on one of your cases, or maybe you just have any sort of project you're working on and you need help from us, always be sure to reach out, give us a call there. Our number is posted here, and I'll also put it at the end of the presentation as well. You also see the support@bre.com. That's our support email that you can send models to, ask any questions that you have about things that you're working on. But I also included there a training email, training@bre.com. Put that there because we are looking for feedback on these webinars. If you find them interesting, if you have any suggestions on other topics that we can lead a webinar on, that would be great to hear as well. And so if you have any questions or thoughts about our training schedule, definitely feel free to email us at training@bre.com. But enough of that, I'll go ahead and get into today's topic. What we'll be doing here today is going to be a bit more downhole than what you're probably used to using ProMax for in terms of the types of models that we put together. So I do want to make sure that we just define some terms. They may be different terminology than you're a bit used to. Maybe this might all be new information for you as well. Wanted to make sure that everyone kind of had a similar understanding of what we'll be doing today. So looking at just a simple well site image here, looking at how the reservoir plays with the wellbore and then with the top hole equipment. One of the things we are going to talk about is the reservoir. That's kind of like the furthest upstream, I guess you should say, of what we'll be looking at today is the reservoir itself and how the oil or gas or both flow through it and some of the fluid properties of that reservoir. The next one up is our well face. So the well face, what we'll talk about today, is going to be the point or the node. Talk about nodal analysis. It'll be a node where the reservoir interacts with the production tubing. So it's considered that point where the two meet, the two interact. And so we'll talk a lot about how oil flows into the well face and how it flows out. And so we'll talk about that term well face. We're talking about that one point there where the tubing meets the reservoir. Next, we have our production tubing. Obviously, once the oil enters the well face, it has to go out, and it goes through the tubing that we've put in through the drilling and completions process. So we have production tubing that flows through. From there, we get to the actual well head. So the head of the well is the top where the actual well tubing turns into production equipment. So a lot of times you also hear this referred to as the Christmas tree because there's a big tree of valves there. And so we'll talk about the wellhead. That's kind of the point where the production tubing meets the facility. Then we have our flow line. That's going to be any sort of piping between the wellhead and the initial facility equipment. We'll look at how to model pressure drops and model that flow line as well, because that'll play a role into our analysis today. And then the last thing that we need to talk about, kind of the furthest downstream that we're going to cover today, is that initial point of separation at your facility. So the initial separator, we'll talk a lot about how setting the properties there plays a role, obviously, in your production level. Focusing in on what we talked about, the well face and doing a nodal analysis, this is going to be the core of what we're going to be covering today, looking at a nodal analysis. And so we're taking the node of the well face and doing an analysis there to see what comes in and what comes out, and trying to come up with some governing calculations or governing relationships to help us do some more calculations in this area. So we'll look at what we call the inflow, which is going to be obviously the oil flowing into this node from the reservoir. And we're going to look for ways to correlate how that flow depends on different properties of the reservoir and different properties of the fluid that's flowing. So we'll have an inflow section, and then the other piece will be the outflow section. So looking at how that hydrocarbon moves from the well face up through the tubing, and then through the rest of the outflow section, which will be the tree, the flow lines, and the separator is all considered the outflow section. We'll look at how to find ways to calculate outflow pressures, outflow relationships. And the idea here is that we'll have two different pieces, and hopefully we'll be able to bring them together to actually do some modeling to make a predictive model of how your reservoir is impacted by the facility equipment. So we've got our inflow and outflow, and one of the things that's important to point out is, in this case, obviously I have directional arrows, right? Because we know that our hydrocarbon in our reservoir is always going to flow out towards our facility, and we know that because of pressure difference. So we talk about trying to establish the relationships here and figure out some equations. What we're going to do is rely on the fact that we know that in most every case, our reservoir pressure is always going to be higher than our well face pressure. And our well face pressure is always going to be higher than the pressure at our initial separator. And so the pressure differences are going to be the driving force for this flow. We will have some things restricting and blocking flow, so we'll have other factors to consider. But the main driver, the reason that production works at its very basic core is capitalizing on the fact that we have a high pressure reservoir and we're setting lower pressure settings in our initial separator, which provides a pressure gradient, which drives the flow that we'll see. So that's a very basic point, but that is one that's integral to looking at the calculations that we're going to dive into. So that's kind of the very basic introduction of what we'll be doing, what I mean when I say nodal analysis, what I mean when I talk about inflow and outflow. So I mentioned that the biggest driver for flow from our reservoir is pressure difference, but we also have some things that restrict that flow, and those are obviously going to make big impacts into the equations when you look at trying to predict the flow patterns. So we have restrictions on the flow on the inflow side, things that restrict that flow and help correlate that flow rate. Things like the actual completion procedures that we set up when we did this, when we drilled the well. So we have things like perforations and gravel packing. The perforations are more related to the completion procedure, how this well was drilled, what sort of techniques were used on the drilling side. But we also have properties of the reservoir innately itself. So the permeability of the reservoir is going to be a defining factor as well. Some reservoirs are more permeable than others, the actual rock, the actual sediment section that we're in, and some are not. And so that will play a role into how easily that oil or that gas can flow through it, the rock, obviously. And then we also have fluid properties. So the actual fluid itself has some sort of viscosity, has some sort of density, and that will play a role too into how quickly that flow can drive through the reservoir and into the well face. So we'll talk about how those factors impact those equations that we'll derive or that we'll at least walk through. But those are some of the factors that we need to consider on the inflow side. On the outflow side, so from the well face all the way through the initial separator, there are more flow restrictions on that as well. And those are a bit more common to what you can model with ProMax. So hopefully those will make a little more sense to the group as a whole. But when we talk about anytime you put any sort of flow through a pipe, whether that's the production tubing or the actual flow line piping, we're going to have some frictional losses, which will define how quickly that fluid can flow, how much fluid you can flow through that tubing. So production tubing friction will be a factor to consider. Flow line friction will be a factor to consider. Another piece of equipment that could impact this is the wellhead choke valve. If there is a choke valve, you'll see it right where you see our box with an X and you have delta PCH for choke. That'll be the choke valve if it is present. Most production facilities have a choke valve there. The idea is that it kind of helps protect some of the equipment to make sure we don't have really large reservoir pressures seep through and get really high pressures on our initial separator. That could be pretty dangerous. It also helps insulate, in some cases, helps insulate the facility operations from the production levels. So we'll talk a bit more about what that means. But when you're in a choke flow setting, the idea there is that our downstream pressure doesn't have as big an impact on our choked flow or the flow that we can force through that choke valve. And so it gives us a little more operational flexibility on the facility side when that's not the biggest determinant on our production levels. So for multiple reasons, wellhead chokes are common. They're not always there. Sometimes the well has existed for so long that the choke is not needed, and so it can be removed. But the wellhead choke, if it is present, will obviously play a big role into what the upstream and downstream pressures on that valve are going to be, what the pressure drop through the valve will be, and how much flow we can actually get through that valve. Another point to consider is the actual set point of our initial separator, the pressure set point. And once again, if we have a choke valve set up properly, then that set point does not become as big a factor on our outflow correlations, but it could play a role depending on how our operations are set up. So we'll talk a bit more about how we can model and predict these correlations on the outflow and inflow side. So when we look at outflow performance is what we'll look at first. And like I said just earlier, the outflow side is something that you could have been modeling in ProMax for a decade now, really, even more. The outflow side is all pieces of equipment that ProMax has been able to accurately model and predict for a long time. And so these are the pieces that you might be more familiar with how to set up in ProMax. And so we'll start here. It might feel a little more familiar to us. So on the outflow side, we look at modeling the production tubing and figuring out what the frictional losses are there. I mean, that really in and of itself is just a ProMax pipeline block. So you'll see a picture of how that will look when we get to the model. The main difference between this pipeline block and pipeline blocks that you're probably used to setting up in ProMax is the fact that this pipeline block is vertical tubing. Normally in ProMax, we're used to modeling horizontal, whether they be gathering networks or just plant piping. Production tubing is a bit different in the fact that there are some different correlations that can be used to model to predict the not only the two-phase flow, but the flow pattern, and then therefore the pressure losses that we would see. And so ProMax does have multiple multi-phase flow correlations that were developed specifically for vertical wellbore oil well tubing in mind. So we'll see some of those when we actually get into the modeling, but I can say that the two that are that I've seen most commonly used in ProMax that from what I understand people seem to use most often in terms of the ones that we have. The one that we use today is called Aziz Govier Fogarasi. And so we'll see that, and that will play a role into how these pipelines are solved. But we also have Duns and Ross, which is another common one that I've seen people interested in. So those would be two different correlations that we can use inside of the tubing, the pipeline block, to accurately model that vertical piping. The next piece of equipment that we'll model is the wellhead choke valve. A choke valve in ProMax it will look just like a regular valve that we could put on the page. And in most times when you use ProMax valves, you're probably used to just setting either a static pressure drop or setting a static discharge pressure and letting ProMax just assume that valve is adequately sized and is the right type of valve for that application. But we do have an additional way to model those valves where we can actually set it up as a choke valve and tell ProMax that it is a choke valve, and it will do some added choke flow correlation and equations there. So just to show you real quick, if you're used to seeing valves in ProMax and going into the project viewer to see what those valves are doing, what you'll notice here, the pressure drop is being calculated for us. Anything in black text in ProMax is calculated. What we are setting, though, is the pressure drop method. And so normally that pressure drop method, the default value is user set, which means you can specify any sort of pressure drop you want. But in this case, we're going to change that to look at a choke valve. And when we tell ProMax that valve is a choke valve and we give it the diameter, you see at the bottom there, I've set a 3-inch pipe diameter. ProMax will then determine what the choke flow is, what the choked pressure drop is, and what size that diameter needs to be to get the flow that we have. In this case, the flow rate is actually being set for us, right? Because in our ProMax stream, we have a set flow rate. And so what we're calculating here is the throat diameter, the diameter of that valve that needs to be set to get choked flow under that flow rate condition. And then you'll see at the bottom in the warning, it actually even tells us that our set downstream pressure is below the choke pressure. So that actually is how we want it to run. Question about tubing. Can we model an inclined tubing run? I imagine what you mean there is something that tubing that is not vertical but is slanted. If it's going to be a directional well, and in ProMax we can probably show that a bit more. We can do different inclines, and that actually will play a role into which correlations are available to you. So some correlations we have are only for exactly vertical tubing or exactly horizontal tubing, because those were the the data sets that were used to develop that. Some are multi-directional. And so, yes, you can set the direction of your tubing. You don't have to assume it's completely vertical or completely horizontal, that you can set up in the pipeline. So we'll show how you would do that when we get to that section. Another good question about artificial lift. My goal at the end, if we have time, is to show you how we could model gas lift. There are other types of lift like ESP that you could also model various ways. That is something that we'll look into at the end of this webinar. So for sure, we'll get to that. Another question, why we allow for pressure increase. That actually is checked by default, I believe, when you open up the valve. In this case, we don't expect to see any pressure increase, so you could disable that. So from the choke valve, we talked about how we have the flow line, and that's once again going to be the piping between the choke valve and the initial separator. And once again, that'll be modeled as a regular ProMax pipeline block. This one will be even more familiar because it is more of the tubing that we're used to, or piping that we're used to modeling in ProMax. So we'll go in and tell it the length, if there are any bends, if it does have a vertical or a vertical bend somewhere, or if it has any sort of reducers, any sort of fittings there, we can go in and pull all that detail into our pipeline blocks, and we'll show you an example of what that looks like when we get our specific model open up for our demonstration. And then from there, the last piece is our initial separator set point. So in ProMax, that's just a regular separator that you'll put in. Most of the time, it'll be a 3-phase separator. You should expect some water, some oil, and probably some gas. Unless it's a strictly dry gas well, you might only have gas and no oil coming out. But in this case, we are going to model a primarily oil well. So we'll have a mixture of gas and oil when it gets to our initial separator. So we take all these process configurations and settings into consideration, and we're going to develop what we call an outflow curve. And this is going to be a big piece to help us relate our outflow section to our inflow. And so the curve here that I'll show in a minute is going to be trying to explain how the different flow rates will affect the well face pressure. So the well face pressure is the outflow section is the most upstream, right? Because the outflow, it starts at the well face and goes to the initial separator. The idea here is that most of the time when we look at our outflow curve, we know the pressure at the top hole. We know the pressure at the initial separator. We know the setting to the choke valve to be able to predict what the upstream pressure of that choke valve is. What we normally don't know is the pressure at the bottom of the well, because we don't have pressure gauges there. We can do what's called a well test, where we actually, whether you have if you have like an ESP artificial lift pump, then that might give you an active pressure reading actually. But if not, then the only ways that we can really do that are to do well tests, where we shut the well in and figure out what the pressure is at the bottom given the flow rate. So most of the time we don't know the well face pressure, and that's kind of the big question. One of the things that we want to look at is how to predict our well face pressure. And so what the outflow curve allows us to do is by knowing the flow of what's coming into our initial separator and knowing all the pieces of equipment, we can see what that well face pressure is at the bottom of our well. And so this curve will allow us to do that. So to develop this curve, actually the way I did it was I took the model that we had, I ran different flow rates through our production tubing and our choke valves, and figured out, given that they always had the same initial separator pressure, what was the well face pressure that was needed to get that. And so what we'll see in a minute is how that curve looks. And we haven't talked much about it yet, so there's probably, if you're thinking about trying to predict how this looks, we'll see in a minute. But the idea here is that as that flow rate increases to the right, our pressure should increase as well, because we have more flow would give us more pressure drop through the well face pressure. So I was going to ask you a poll on this, but I figured this might be a little too difficult to predict. So let's just go ahead and look at the curve itself. You'll see for our outflow curve, in most cases, for most of the flows that this well is producing under, as you increase the flow through that outflow section, the well face pressure will increase as well, which means we're getting more pressure drop. So if you put more oil through a pipeline or a production tubing, you're going to get more pressure drop through that tubing, which makes sense, right? That's what we see in almost all cases, and no matter what sort of piping you're talking about. The more you put in it, the more pressure drop you're going to get. And so knowing that outlet pressure is static, the only way that pressure drop can be reflected is by having a higher delivery pressure or higher injection pressure from the well face. There is a slight section where that curve does double back on itself for reasons with the fluid properties. And so sometimes you will hear the outflow curve called the J curve. it is somewhat common to see it have that uptick. Not always, but sometimes it does. Having to deal with flow regimes and the physical properties of the fluid itself as it gets to lower flow rates. But in most cases, what we'll see is that more flow through our well will give us a higher well face pressure. And that's the big takeaway here. More flow would equal a higher well face pressure. And so in a second, we'll look at how that affects the inflow, but we do need to talk about the inflow performance. This is the looking at the inflow section and trying to find an equation to govern how that flow is structured. And so this is actually the new section to ProMax. I say new, we've had this in ProMax for about a year now, ever since ProMax 5.0 came out. We've had an inflow performance relationship analysis. So IPR stands for inflow performance relationship. So looking at the relationship of the performance of the flow. It really is all it is. And so IPR for short, I'll use IPR moving forward. ProMax has several IPR correlations, and they all are governed by this simple generic expression, which is that the flow rate of the oil is dependent upon a few properties. And this once again, this flow rate is what's coming out of our reservoir. It's governed by the reservoir pressure, right? And the well face pressure. So once again, that's how we talk about our driving force. The larger difference in pressure between those two, the more driving force that hydrocarbon has to flow towards the well face. But then there are some restrictions involved, and we'll tie most of the restrictions of the inflow section into a coefficient called J, the productivity coefficient. And the idea is that J will be a catch-all for the more intricate things of the well, like the permeability of the rock, the perforations in your tubing, things like that. So there are more complex ways to coordinate those, and there are more complex equations that have the ability for you to give it, like a number of perforations and a permeability of your reservoir. But in a lot of the IPR correlations that we'll see, they will tend to tie all of those into one coefficient called the productivity coefficient. But then the question becomes, well, how do you know what that coefficient is? In theory, it should remain relatively constant because the permeability of your rock and the perforations of your tubing are not changing much. And so it should be a relatively constant property. So once we can find it from one given data point, we should be able to apply that as a constant coefficient, at least in a relatively short given period of time. And so the idea here is that what we're going to do is we're going to use what's called a well test. A well test is, once again, we talked a bit about it before. Well tests are common for E&Ps to take. The idea is that we'll have to figure out one given set period of time what the well face pressure was and what the flow rate was. So normally a well test, like I said, if you have a pump, a lift pump, that might give you a live pressure reading, but if not, you'll have to shut the well in and figure out what that downstream pressure is, that downhole pressure is, given the flow rate that you were flowing, and that will be considered a well test that you can use. And so most of these, every correlation that ProMax has, every IPR correlation, will require at least one well test data point, and that's to do the initial calculation of what that J coefficient is. And then from there, we can use that constant J with new different pressures to see what that flow is going to be either in the future or what it is now, given that the well test was taken X number of months or years ago. So I said there are lots of different IPR correlations that are out there. They all have a general relationship there, but the intricate pieces of the equations are a bit different. So in terms of oil wells, we actually have 4 different IPR correlations that you can use. I believe the default is the Vogel correlation, and that's the one that we will use today. The question of which one to use is a very detailed discussion that lots of even textbooks that I've seen will have detailed discussions on which ones are best for which case. So it is a pretty involved question that we would definitely need to talk to someone experienced to know what that means. But so the correlations here, we have 4 different versions for the oil well, and then if you have a primarily gas well, there are also different correlations to define those as well. And so we have 2 of those in ProMax. So on the inflow performance, once again, we're going to set up an equation that's going to give us a curve, an inflow curve, and we're going to compare it to the outflow curve. And so on the inflow side, the question becomes, if the flow rate's increasing in the reservoir, is that due to a higher well face pressure or a lower well face pressure? So on the inflow side, it curves the opposite way of the outflow. The idea here is that in order to get more flow out of your reservoir, you need to have a lower well face pressure. So as that flow rate increases on the X side, our well face pressure is going to decrease. A lower well face pressure is going to provide more driving force, which will bring about more flow into that well face. And so it's the exact opposite as the as the outflow side, right? So more or a lower well face pressure and more will give you more flow on the inflow, but also will restrict you more on the flow going out. And so we have basically here two different equations that produce two curves, the inflow curve and the outflow curve. And we have two unknowns, which is the well face pressure and the well face flow. And what we'll do is basically take our nodal analysis will be the process of taking these inflow and outflow equations and figuring out where they meet. And so we have our inflow curve here. We overlay our outflow curve on top of it, and you'll find the intersection point. And that is where you are currently operating, given all the properties that you put in about the composition of your and the properties of your fluid, given the size of your production tubing, given the well test data that you gave us, giving all the properties that you know of that well. This is how we determine the operating point, is by overlaying those two curves on top of each other. Basically a system of equations, two equations, two unknowns. You find the two unknowns with that. We also have a good question here to determine whether you have a gas or an oil well. The idea there is that a gas well will always be single phase. Normally what that means is if your reservoir fluid exist as a pure gas at the reservoir pressure, since that's the highest pressure you'll see through this process, then you'll have a gas well. If at the reservoir pressure, your fluid is either a two-phase or 100% oil, then that will be an oil well IPR. That's a great question. So you'll see our operating point in this case, given all the properties that I gave. What that means is that we're operating at about 1530 PSIG at the well face. And in doing that, we have about close to 1,400 barrels a day coming through that facility. And the beauty of the analysis here and setting up these correlations and defining the curve is that we can now change any property that helps set these curves up and figure out what the new operating point is going to be. And so whether that's a future, maybe you're planning to change some of the way your production tubing, maybe you're going to change your tubing size. Maybe you're going to cut back on your choke valve setting and open that valve a little bit more. That's going to change the nature of the outflow curve. And then we can find the new operating point by just comparing these two together. So this now becomes a predictive way to figure out any changes in your system and how that's going to affect the production that you'll see. What we'll do here is we're gonna go into ProMax to set that up, but I do want to just cover what data is needed to set one of these models up so that you can understand what you would need if you wanted to do this yourself. And we will go from furthest upstream to downstream. So from the inflow section to the outflow section, what information do you need to set one of these models up? We do need the well fluid composition. The composition of the well fluid plays a big role in all of the physical properties that govern the inflow and outflow performance. So normally you get that one of two ways. If you have a PVT on hand, then we can use your PVT analysis to find the composition. PVT analysis have composition in them, so that's a test that you can run that will give you information about your well stream fluid. Or if the only samples that you have are further downstream, let's say you have a pressurized liquid sample or maybe your oil sample of what you're selling, and you have your sales gas sample, we can do a procedure called back blending to get that well fluid composition. And that's something that we cover in several of our training classes. So if that's the situation you find yourself in, we're definitely able to help you back blend your samples to figure out what the well fluid composition is. But one way or the other, we'll need to know that composition. We will need to know what your assumed reservoir pressure is, with the understanding that that obviously helps with the driver of the inflow performance. So the IPR correlation will need a reservoir pressure before it can calculate. We will need a well test data point. And in parentheses here are the values that I'm going to be using in our model. So I'm going to be using an assumed reservoir pressure of 2,400 PSIG. And the assumption also is that at one point on this well, we took a well test and it was running about 710 barrels a day and it had 2,000 pound well face pressure. And one thing to point out too, the well test data, that pressure is the well face itself, and that flow rate is the combined flow rate coming into the well. So on the well test, we're looking at the inflow section. So the well test doesn't care when that oil got up to the initial separator, how much it was oil versus gas. It's looking at the actual flow rate going into that node, and most of the time going into that node, it's either mostly all oil or all 100% oil going into the well face. But either way, we're looking at the overall flow rate of the hydrocarbon, whether it's gas or oil, is what that flow rate is. From there, we do need to know the properties of the production tubing, so the size, the length, obviously, if there is some angle to it, what the angles are. If you have like a deviation survey, is what that typically will outline. We can take that and use that to define the production tubing. We do need to know from there what the choke valve throat diameter is set to. So on the choke valve, most choke valves have manual settings where you can set that throat diameter pretty easily between different values. And the general convention is to look at that value in 64ths of an inch. So if my choke valve setting is 28, that means that my actual choke valve throat diameter is 28/64ths of an inch. So we're assuming in this case that we know our facility is operating at a 28 choke valve setting. So we're going to want to see that in our model. We do need to know the properties about the flow piping, the flow line itself, obviously, set those up. And then one of the things that will also be important is the initial, the separator pressure. So what set pressure is on that initial separator? Most of the time that is governed by a control valve on the gas side. If your gas is directly set up to go into a gas pipeline network, then you normally insulate the delivery pressure into the pipeline by putting in a control valve there. So most of the time we have a pretty good control of what that initial separator pressure is going to be. And then also we want to know the flow rates of that separator. So how much oil, in this case, we're looking at the oil, the gas, and the water all separately. What's the individual flow rates of all three? And we'll put all of this into the model, but the two big ones that are used to validate the accuracy of the model are going to be the choke valve diameter and the initial separator flow. In ProMax, what we'll see is that we can use what's called a ProMax solver to directly ensure one of these is right. So I can put in a solver to make sure that my flow rate is going to be exactly 700 barrels a day. But if I do it that way, then I won't have any ability to set the throat diameter. And so then at that point, the throat diameter would be a way to check the accuracy of the model. So I'll drive it directly to 700 barrels a day. Then I'll compare the reported choke valve diameter to the one that I know to be true. And if they're close, then that means this model is pretty accurate. If they're further off, then we'll need to look into some of the information that we set in. Maybe the composition's out of date. Maybe the reservoir pressure has changed. Things like that we're putting in. Maybe those assumptions need to be reevaluated. And vice versa. I can instead directly target a throat diameter of 28/64ths of an inch and then compare my oil flow rate and make sure that it's close to 700 barrels a day. So those are the two that are going to be big in figuring out, okay, is this model working properly? Can we trust it? Yes or no? So I'll go ahead and open up a model that I've set up for this exercise. Surely familiar because we've seen bits and pieces of it as I've gone through my presentation. But we'll see what will kind of be a comprehensive view of our production tubing all the way through our initial separator. So we do have a reservoir hydrocarbon stream and water stream. We separate those because the IPR correlation specifically is related to the oil flow rate. It does not have any bearing on the water flow rate. So we will need to add our water in separately with a oil-water ratio, OWR. We can set up one of a specifier to do that and set up our water flow rate given our oil flow rate. If you're familiar with ProMax, you know that red streams mean that we don't have enough information. So I have not put everything into this model yet. I'm going to walk through some of the important pieces that are either new or interesting to this setup. So my reservoir hydrocarbon stream here is my inlet. We always start with the inlet streams in ProMax. So I want to make sure that I have everything specified that I need to in this stream so we can move further down. So my reservoir hydrocarbon, if I double click on that, it'll open up our project viewer where we'll see the properties of our stream. So I do have a temperature set there of 170 degrees. I do not yet have a pressure or a flow rate set up because those are the two properties that our analysis are going to help us to determine. So I don't have those set up yet. I do, on the other hand, have a composition set up. So you'll see the composition there is determined for me. In this case, we have some light ends specified, and then we are using what's called single oil to specify our heavy ends. Depending on your sample, you might have a curved oil that you would need to employ, and we can talk about the differences there if you have a real case set up. But one important piece is making sure we get the composition accurately specified. But like I mentioned, the pressure and the pressure and the flow are things that we're going to use our inflow and outflow properties and equations to determine. So the way to do the inflow side, the IPR analysis, that's the new piece that I mentioned that we've had for about a year now. That's found under the stream analyses. So if I go to the analyses tab at analysis, we have one called oil well IPR analysis. So this analysis is like a separate calculation that you can do along the side of ProMax. And this is where we have all of those correlations housed. So our inflow performance relationship here, I mentioned we're going to be using Vogel. So I'm going to select Vogel as our option for this case. The temperature is coming in from the stream. So I set the stream temperature and it's going to assume that that's what I want. And my static reservoir pressure, I mentioned that I'm going to have a reservoir pressure of 2400 PSIG. So that's where I'll tell the model to use that. And we did have a question earlier about the PI. If what you mean there is the productivity index, that is what's being calculated from our correlation. It's similar to the J productivity coefficient. I think it's a bit different in terms of the actual way it's determined and the way it's presented specifically in the units that it uses. But the productivity index is something that's calculated using the well test data and the specific correlation that's at play. So it will be determined for us. So you see all these gray cells are things that ProMax will calculate for us. So we set our pressure, we set our IPR relationship that we want to use. The last thing we need to do is set in our well test pressure. I believe that we used a test of 2,000 pounds and 710 barrels per day. So let me open that back up. 2,000 PSIG and 710. Now that I have that well test, we can actually go through and actually set up our specific data point. And so what we'll do here, you'll see we have a present bottom pressure that we can specify and calculate the flow rate or vice versa. So I'm going to, first off, I mentioned our well test here was at 2,000 PSIG. I'm going to assume that currently we're going to make the assumption, and we're going to definitely go back and correct this, but we're making an initial assumption of what that well face pressure will be to determine what our oil flow is going to be. So I'm going to assume an initial well face pressure of 1,800 PSIG. And then from that, using the correlation and the inflow curve, ProMax can tell us what our oil flow rate currently is. So once I have that set up, I can click Solve, the top right. I got a good question here from Ariella about the future IPR. So there are some of the IPR correlations that are used in ProMax do have a separate way to predict your future IPR. The future is looking at changing the actual reservoir pressure for the future and how that changes the correlation itself. Not every correlation has the ability to do that or claims to have the ability to do that. And so there are only two options here for the future IPR method. Most of them will require more well test points. So you can look at like the future of your reservoir through some of these correlations, and that's what that section is used for. We're not going to dive into that much today, but that is something that you can use as well. But that's why it's different here, is because Vogel actually doesn't even have a future correlation method calculation. So I assumed that my well face pressure was 1,800 PSIG. That's a lower pressure than my well test, right? My well test was at 2,000. And so what makes sense is that we would see a higher oil flow rate, right? Because lower well face pressure will give me a larger driving force across that reservoir and give me a higher oil flow. And so our well test was at 2,000 PSIG and it only had 710 barrels a day. You'll see at the lower pressure, we have 1,022. So we do have a higher oil flow. So this is working correctly. You can actually see, if we go to the plots tab, you'll see a plot of that inflow curve. And on it, you'll see our well test point. So this red square is the well test point that we use to actually figure out how to put that curve on the plot. And then we'll see our light blue line here, our dot, is our current operating point that we with the assumed 1,800 PSIG well face pressure. And you will see the reservoir bubble point pressure here. So if we are above our bubble point pressure, or sorry, yeah, if we're above it, then we're in a one phase region, single phase. If we're below it, then we've actually got some bubbles and we're in a two phase region. So with that information, I now have an assumed pressure and my oil flow. I can go back to my properties tab and see that once again, we don't have a pressure set and we don't have a flow set. And so we're going to use the IPR analysis. We're going to tie that to the actual stream data so that whenever something does change by our reservoir, let's say we change our well phase pressure, that flow rate is always going to update to what the IPR tells us it should be. And so actually to do that, what I'm going to do, I'm going to delete the pressure inside the analysis. The analysis is trained to know if I set a pressure in the stream to use that. And so what I'm going to do is set a stream pressure here of 1800. And you'll see in our analysis that will flow into our analysis, or it'll be given the pressure from the stream. And then once this is solved, I can actually take this oil flow rate and directly put that into the flow rate of the stream. So I'm actually going to right click and add that moniker to my clipboard. I'm going to create what's called a simple specifier in ProMax to do this. The goal here is not to show you how these specifier solvers work. I'm going to kind of just quickly set these up. If you have questions about solvers and specifiers in ProMax, definitely let us know. That's something that we can either go through. You can attend one of our training classes to see those, or we can do a one-on-one session and show you how those work. But what I'm doing here is setting up a specifier such that anytime the predicted IPR flow rate changes, that our actual stream flow rate will change as well. So it'll be a live update. So now I can solve my flow sheet and see that 1022 there is the exact answer coming from our IPR. So now what that means that if I were to go in and change my pressure here, say 1805, that analysis is going to pull it in. And if we solve the model, it'll solve that IPR equation and it'll give us a new flow rate. So this flow rate now is always going to be updated. We're taking the pressure, running it through our IPR equations, and then outputting a flow rate. And it'll always stay constant. It'll always stay, I guess it'll always stay with what the IPR correlation predicts, I should say. So now that we have a pressure and a flow, we have everything that we need to know about this stream. If you go back, we'll see that since I executed the flow sheet, our hydrocarbon stream's green. Our water flow rate, we have a specifier here giving us our water flow based off of our oil-water ratio. So once again, if you have questions on setting those up on your own models, let us know, but that's just using a specifier. We're also using a specifier to make sure that the pressure of this water stream is the same as the hydrocarbon, because in reality, these are in the same reservoir, they have the same pressure. So that's the IPR, that's the inflow section, is doing the IPR correlation and linking that to our stream. The second half of that is the outflow, and that's where we have all of our blocks here to specify that information. So I'll just quickly show you kind of how that was set up. But once again, the goal here is not to teach you how to do this. It's just to kind of show you that it's there. And if you have a real case, definitely let us know and we can help you more in a one-on-one setting. So our production tubing, it is a pipeline block in ProMax. We've set up that it is 6,000 feet long. In this case, we are setting an inclination angle of exactly vertical, but you can change that angle. So I think someone asked earlier if you can set different inclined tubings. So you can change the inclination angle here to whatever you need it to be. So we can change that if it is going to be going more horizontal as we go down, we can change that angle. We're also giving obviously the diameter of that tubing to know how much area we have to flow that fluid through and therefore determine the frictional losses. And the options section is where we can set our multi-phase flow correlation. So given that we have a 90-degree inclination angle, we have some options as to what to use. And we're using the Aziz-Goviev-Verassi equation in this case. And then we do set up some heat transfer properties as well to figure out how the area around the tubing is either pulling or adding heat to the system. So knowing the temperature inside the pipeline, inside the contents of the pipe, we can predict that flowing correlation. One thing that's different here than what you might be used to is that normally when we look at pipe surroundings in our heat transfer, if it's a vertical or it's a horizontal pipe, whether it's a gathering network or plant piping, we normally either make it buried or above ground. But if you use buried wellbore, that is the given heat transfer equations that govern vertical wellbore flow and how the heat transfer is derived there. So that is a different setting that you're used to. Probably want to make sure to use buried wellbore. If you do that, one of the properties you need to set is the time that this well has been flowing. Because if this well is brand new, then the actual temperature of the surrounding ground is probably more like what it is before a well was drilled, just the general temperature gradient of ground in that area. But if your well's been flowing for a long time, and let's say that the well fluid is hotter than the actual surrounding ground, then over time that ground temperature is going to drive closer to the actual temperature of the reservoir, and you'll get less heat loss. And so that's the idea there, is that this correlation can take that into effect. The amount of heat transfer at the initial infancy of the well is going to be different than if it's been existing for days, months, or years. So that is playing a role here. Everything else here is just looking at results. So we can look at that point, the results tab will show us things like the pressure drop that you see at each point. In the increments, though, we'll see a bit more detail. We'll see, obviously, temperature pressures. We will see the two-phase information. So you'll see what's called a flow regime. And we're definitely going to cycle back to the flow regime to see how that plays a role in our production performance. But a flow regime is based off of obviously the amounts of liquid and gas in the pipeline, but also the superficial velocities of those. The velocities of those will play a role into the flow regime. So if you have two-phase, in this case, we have a constant two-phase setting, you can have a bubble regime, which means that our gas is flowing fast enough that it's actually shearing the liquid, and there's just bubbles, slight bubbles. Actually, the bubble would be mostly liquid. So the liquid is the primary phase, and it's actually pulling up bubbles of gas with it. So that's what bubble would mean. But a slug would mean that we actually have probably a higher velocity vapor, to the point that it's actually channeling the vapor, and the vapor's flowing up, but the liquid is caught in these larger slugs. And slug flow is a big problem with vertical wellbore tubing. It means that your well might be loaded, which means that the gas is coming up, but it's not adequately driving up the oil. And so your production rates of your well are going to normally take a steep drop down, a steep dive, if you are in a slug flow case, and that's when we call your well being loaded. And that's a lot of the reason why we have things like artificial lift. So when we talk about artificial lift, it'll be looking at this flow regime and figuring out how to change that. One quick question, cycling back to Mariella asked about the well test pressure. The idea behind a well test is that it was taken some period of time ago, and so it was accurate for the time that we took that well test, but it's not accurate anymore. So just because our if we go back to that analysis, just because our bottom hole pressure was 2,000 pounds back when we were producing 710 barrels a day of oil, we probably are producing a different amount, right? Because most of our wells have decline curves to them. And so we're probably producing a different rate, and therefore have a different well test pressure, and don't know what that is. So that's the purpose of this correlation. So from the tubing, we have the choke valve. Just briefly touch on this since we've already shown you what that looks like. We are setting the pressure drop method to choke valve. The default here is normally user set. And then we're going to be calculating the throat diameter here. So once again, this is one that I said we know this exists to be 28, so we want it to equal as close to 28 as we can when everything's all said and done. We're already pretty close because, spoiler alert, I used a pretty close initial pressure guess of 1800. That's pretty close to where it's at, but we'll see how that changes as we set those things in place. Then from there, we have our flow line. Once again, it's just a pipeline block. We can go in and say that it's 1,000 feet of tubing, or a piping, I should say, give it its size. If you have more bends and turns that you want to add, you can add more segments and put in elbows and reducers, all that kind of stuff you can do here if you need to get that level of detail. And then we have our initial separator. So initial separator, in this case, what we're doing is we're setting the pressure coming into that separator of 200 psig, and saying that the pressure here, pressure drop is 0. Basically saying that our pressure drop actually is, our pressure drop is 200. Sorry, not our initial separator. That's an interesting. This might not be set up the way that you would in reality. I don't remember actually why that is 0. We don't have an initial separator pressure of 0. Maybe we did that for a different analysis somewhere along the way. All that to say is you put in the pressure that you see at the separator. Normally in your outlet stream, you can initially set that pressure. And from there, we'll be able to basically back calculate the flow rates that you see. So that's a very brief introduction to all the different ProMax objects. Once again, if you have any questions on those, or if you're trying to do those in real life, definitely let us know. Part of what we really like to do is provide that support alongside this. So this is hopefully just to get you thinking, get the wheels turning, and then we'd love to help you do one of these in real life. So I mentioned earlier that we want to make sure that we have 700 barrels a day of oil coming out, and we have a choke valve setting of 28, and we can only do one of those two. I mentioned even earlier that we're going to do what's called a simple solver in ProMax to get that. So actually, to show you how that works, we're actually pretty close to the value. I'm going to change this hydrocarbon pressure here. So once again, I said this pressure is assumed, and we were going to go back and change it. Let's say instead I assumed a pressure of 1750. And I executed that flow sheet. So with an assumed well face pressure of 1750, that therefore changes the flow rate that goes into our well face from the IPR, and then changes obviously the different amounts of oil that we get, what the choke valve setting needs to be. So now we see that our oil is 748. It's a bit higher than what it should be, right? Because we want 700 barrels a day. And our choke valve setting is 29.8, and we want it to be 28. So they are a bit off now. And what we're going to do is we're going to say, well, we know what we want those values to be. We're going to use a solver to drive that. So anytime you have a expression or some sort of check property that you know needs to be true, we can use a solver to iterate to get to that point. So what I'm going to do is put a solver on top of my pressure, and my solver in this case, I'm going to attach it to the oil flow rate. So I'm going to say, we don't know what this pressure is. We want ProMax to vary it until the oil flow rate equals 700 barrels a day. And that's what our solver will allow us to do. For doing that, I'm going to go to my oil here and go to the flow rate. We want that to be in barrels per day. I'm just going to copy that moniker to my clipboard so I can reference it inside of my solver. So I'm going to create a solver here. This is going to add an iterative process to my model, and it's going to make some steps in different directions in changing the actual pressure to give us to determine what steps it needs to take, if it needs to make the pressure higher or lower to get closer to the value that we want. So we tell it that we want our oil flow to equal 700 barrels a day. That's setting up our expression, and it's going to change our pressure that we're sitting on top of until it drives that value. So now that that is set up, I can go back and execute my flow sheet. You'll see that it'll take different guesses to see which direction that pressure needs to go, if it needs to go up or down. And it will determine that we need to go up to get less flow rate, right? Because we have too much oil in this case, more than what we're producing in real life. So a higher well face pressure would give me less oil. So it's going to say now it was at 1750. Now it's much closer to 1800, which is what I had it initially set at. And we'll see our oil flow rate here. If I open it up, will directly be exactly 700 barrels a day. So basically what I just did there was the equivalent of overlaying those curves on top of each other and finding where they intersect, right? Because we know that those at the intersection points where we're actually operating. And so we're driving to actual operating values. I'm basically tying the two curves together and using a solver to find where those two curves intersect each other. That's the general idea. At this point, I mentioned we derived exactly 700 barrels a day of oil. The last check that we have is to make sure that our throat diameter is close to what it should be. So I open up my choke valve, and it's at 28.07, 64/7 inch, which means that we're right on top of what we should be. So that once again, this is the point where hopefully at this point, when you do your real case, that value check is very close to what it should be. If it's not, then maybe we need to go in and look to see, do we need to use a different IPR correlation? Do we need to get an updated sample? Maybe we're using a PVT that was taken 4 years ago, but we can use a backplitted sample that was taken 6 months ago. That probably is a bit more accurate to the actual composition going through here. Maybe we need an updated well test point. Maybe we need to go check to see if a well test was taken earlier or more recently than the one that we have. There's lots of different things we're putting in here that we might need to change around if our model's not accurate. But seeing that this value is very close to what we know it to be in the field is a very good way to validate that the model's working properly. So at that point, this becomes, like I said, a predictive model where we could go in and change different properties. Maybe we want to look at, well, maybe we want to target 750 barrels of oil. Let's say, well, how far back do we need to pull back our choke valve to get to 750 barrels? And so we'll see here, obviously our choke valve right is at 28 and I'm getting 700. Maybe I say, well, I want to change that because I need to make more oil. And I'll go into my solver here and say, instead of 700, I want 750. If I want to do that in the field, what does my new choke valve setting need to be? I need to go tell the operator to move that valve. What does he need to move it to? And we can execute that flow sheet to see if we're just changing the choke valve and all the other properties are staying the same, what gives us 750? And what we saw when we had it originally at our pressure was at 1750. We're much closer to that. So you'll see now, in order to get more flow, I need a lower pressure, right? I need 700 or 1750 instead of 1800 To do that, I need less pressure drop in my system, right? Because this pressure here is determined by how much pressure drop we get as we go through this piece of equipment. So to get less pressure drop, I would probably need to open up that choke valve a bit more. What is it going to be open to? That's the question. And so I open up this choke valve block to see what that looks like. It's like now we're much closer to 30 instead of 28. So we would tell our operator to go out and set that choke diameter to 30, and that should give us closer to the flow rate that we want to see. Another thing about ProMax too is we are able to tell that value is still in a choke setting. And so we'll actually, if I go back, we'll set it back to the original set point of 700. So you'll see here that when I am set at 700, I do get a warning at the bottom, which tells me that my downstream pressure of 205, which that is coming from just knowing that this is 200 at the separator and knowing what the back pressure of the flow line is. So ProMax is back calculating what that pressure before the flow line is. It's 205.8. And what we're saying here is that 205.8 PSIG is less than the onset of choke flow. Choke flow occurs at 216 PSIG. So in this case, we actually tend to like choke flow because what that means is that I can change the pressure at my separator here. And if I say I need to increase that pressure from 200 to 205, that shouldn't play a role in actually changing my production level. So it kind of insulates my facility operation from my production operation. And if we want to change our production level, that's when we go to the choke valve, not the initial separator set point. But in this case, we are pretty close to that choke flow. So you just saw when I changed that to 750, it did not give us that warning, which means that we were not choked. So that would not be a great way to get more production, because we would then be taking our choke valve out of the equation, and the way our separator runs, which is normally based off of our gas gathering operation, would then directly tie us to a flow rate, a production rate that we may or may not want to operate at. So chokes are normally a pretty good idea because it really helps us to be able to make decisions in different areas and make them separately from each other and not have unexpected outcomes. So that's one thing you need to consider too, is we can't just keep opening that valve and keep getting flow if we want to stay choked. So lots of different things that we can do here, lots of different things that we can analyze. And that's why we're getting these discussions to kind of show you some of the examples of things that you could use this model for. And the last one I'm going to do here, I'll try to make sure we get out close to 11:30. The last thing that we're going to do is add gas lift. So the idea is in our production tubing, we had those slugged flow regimes. And normally slug flow is a bad thing because it means that our oil actually isn't flowing out of the well. So in ProMax, we're assuming that the fluid is always flowing in the direction that you want it to. We don't assume any sort of backflow. But when you see something like a slug flow, that's telling you that what you see in the field is probably not going to mimic what you see in ProMax, because the slug flow means that there's a good chance that liquid is going to form large volumes of slugs and then therefore drop back into the reservoir. And that's obviously not what we want if we're trying to produce oil. So that's where you need some form of artificial lift. And the one that we're going to model is gas lift. And the cool thing about gas lift is that normally the gas is coming from the gas that you produce in the facility. So we can actually directly tie our gas lift system to the gas that we are producing and see how much gas we would need to drive that proper operation. So what I'm going to do is take a split stream of that gas, run it through a gas lift compressor, recycle it back into my well face, because normally the gas is cycled back through channels down to the bottom of the well and brought back up. And we're going to see how that plays a role. Put that 0 for now. How that plays a role in our system. So as of now, the flow rate is 0. So 0 flow through that split stream. That's why these blocks are gray. So this is exactly like the operating before. But now I'm just going to say, I'm going to go into stream 2 here. I'm going to assume that we have 50,000 standard cubic feet per day of gas going into our gas lift system. I'm going to see, is that enough gas to change my flow regime such that I'm not in a slugged flow. So I'll now therefore re-execute my flow sheet. That recycle is going to add that gas back in and see how adding the gas is therefore going to increase the gas velocity and the gas flow rate. And hopefully that means that it's going to actually start to shear the slug and form more of a mist flow regime. And so we'll see, open our production tubing, and we'll see that we have not gotten to that point yet. We still have slug flow. But the idea is that as you increase more and more flow into that, more and more gas lift in there, you're going to get enough gas velocity such that you'll start to see a mist pattern. And the question becomes, well, how much flow do we need to get to that point? And that's where a model like this comes in a big way, because we can do something called the scenario tool to do that. So once again, scenario tool is a tool in ProMax that I won't really go into the nuts and bolts behind it. But the idea is that it's a tool that we can use in Excel. So I have an Excel sheet here that's already embedded and connected to my project. And what we're going to do is we're going to vary the flow of our gas lift. And we're going to see how that affects the regime of both the bottom section and the top section of that well. And we're going to see how that changes some of our other properties too. So I think that this is already set up here. Yep. So I've got my scenario tool set up where I've linked those properties together. I have 7 different runs. So it's going to run through and just make these, change the flow rate of that gas lift, and then report what we need to report. So we can see how that plays out. And for the sake of time, I'll let this run in the background, but I'm also going to pull up a finished version of it as well, just to show you what that looks like. Well, before I even pull it up, this actually might be solved. The other model I was pulling up at the moment, but you'll see here that it's actually not taking too long to get through. So as that gas lift amount is increasing, we're going to see some changes to our regime. So at first we had bubble at the very bottom, which means primarily liquid, but now that we're adding more vapor, it actually has to first go through a slug. But the idea is that eventually we'll get enough gas in play that we'll get some different regimes, and we'll go from a slug through a transition to a mist. So in this case, we'll see that we need about 1,500, I guess it's about 1.5 million standard cubic feet per day of gas. And when we do that, and I can go back to my ProMax model to show you, to verify, this is still on that last scenario we ran. We have a fully mist regime flow, which means that all of our liquid is actually being adequately brought up with our gas. So that would be a way to properly operate. So the question then that we've answered is how much gas lift you need to have. That is going to play a role into how much, if we're recycling a lot of gas here, that means that all this equipment its gas flow is going to change. The initial separator is the biggest one, that it's going to have a lot more gas coming through it than it initially was expected to have. And so one thing that you also could use ProMax to do that is probably a good idea is to make sure that our separator is properly sized for that. So in ProMax, you can size separators. I'm not going to get into that today, but it's just another idea of what you need to, things that you need to consider that you can use ProMax to do, is to make sure that our separator with its initial sizing can actually still handle the increased amount of gas going through it. Because at first this was about, I think, 0.6 million. Now we've got 2.1. So a lot more gas coming in, almost 4 times as much gas coming in. That's going to need to be considered that before just assuming that it'll work. Question says that the choke valve is fully opened. How can I find an optimal gas injection rate to get maximum oil production? What you would do at that point is you actually probably wouldn't run any sort of solvers because you're wanting to vary the oil. That's actually another thing to point out too. There's different ways we can run this analysis. So once again, I still had my flow rate targeted to 700, which what that means is that I want to know, okay, when I get the lift, I still want to only produce 700 barrels a day. So that's a choice I'm making when I'm operating and saying, I'm targeting 700 barrels a day. Maybe I have a downstream limitation on my piping, or my trucking capacity is restricted. And so I'm also going to change my choke valve setting to get there. Another thing you could have done is said, I don't want to touch my choke valve. I want to keep it at 28 and see how the oil flow is going to change from the added gas lift, which is more like what you're asking for, Vincent, is keeping the choke valve setting constant. If it's completely open, that's fine. And then seeing how the oil flow is going to change. And then you should see then how that oil flow, it might have a peak where you have an optimal point there. And so that's how you would probably set that up, is to just change what you're targeting. So right now I'm targeting a flow. I would target a choke valve and then let the oil flow tell me what it's going to be at different amounts of gas lift. Question about can you please tell us the impact of production due to gas lift pressure? That's a great question. The actual pressure of our gas lift, we're determining that from a compressor, right? Because most of the time when you have a gas lift, you're taking a low pressure gas from your production and you're cycling that back through it. It needs to be compressed, obviously. And so the pressure you assume is coming off of that compressor, in this case I'm doing 2300, does play a role as to what that pressure is when it's mixed. And so that, if you'll see here, this whole face pressure is actually, it's not changing that much, 1798.2, so 10.8 point. Oh, so actually isn't changing. Oh, that's okay. Yeah. So that's actually something that we could change. The idea here is that this compressor probably needs to inject the gas at the pressure of the well face. And so we would either need to make sure our compressor is compressing it only to the 1798. Otherwise, it might start to inject gas into the reservoir. Or we can actually change the well face to where its pressure that it's driving is the pressure of the gas lift. So we could change that in a few different ways. And when you talk about the impact of production due to the pressure, that's something that we would change the pressure that we're using, the well face pressure. We would actually look at what that is based off the gas lift compressor. And then once again, we could run some scenarios to say, if we increase the pressure of our gas lift, how is that going to affect our production level? So that's something that you could use the scenario tool to do if you had the model set up to do that way. Bevan also has another good question. Does this always require the gas to be injected to the bottom of the tubing? The answer is no. We can set it up to where we can have different injection points. The way you would do that is probably you would split our production tubing block into several different sections. So let's say, I think overall right now it's about 5,000 is the 6,000 is the length. So we say we want to do 3 different sections of 2,000 feet each. And then we would have different nodes that you can actually vary. You can actually put a node, a mixer block in between and say, well, what happens if we injected it at the slightly higher injection point? How does that going to affect things? Because you're right in the fact that I mentioned that most of the time, the goal of the gas lift is to at least eventually flow all the way to the bottom of the well and come up. But that isn't always the case. If only a certain section of tubing is the problem that you're seeing, then you can actually inject at a midpoint, and that would help you eliminate or minimize your compressor power, because you don't have to get all the way to the very bottom well face pressure. You can get to some intermediate pressure, and it would just affect the efficiency of the tubing as well. So that's a great question, Bevan. We can actually add different mix points, vary the pressure there to say, okay, maybe we can mix this midway through, still get the flow regimes we want, and drastically reduce the compressor power that we need. So that's another great question that we could use the model to either prove or disprove. But that is the end of what I had planned to cover. I just wanted to put back up, just let you know that we do have, once again, the support email that you can email to if you have questions about a model, whether it's IPR related or not. And once again, like I said, if you have any sort of opinions on our training schedule, webinars you want to see, or training classes you want to see, definitely let us know at training@vre.com. Definitely encourage you to help us by interacting with us on LinkedIn. Thank you so much for attending.